I'm now beginning the recording, which is going on YouTube, and I believe I should be heard here by external people as well. Okay, so let me get some slides up here on the board for us to look at. Okay, so the goal of this class is to try to help students learn how to build, critique, understand, and use simulation models. These are models that simulate out a system over time. This system could be anything from a large collection of computers that's depicted to aspects of the healthcare system, to aspects of biology within a person. The simulations that we're going to be working with within this course fall into three broad types. The first is a type of simulation known as system dynamic simulation, which is traditionally a fairly high-level depiction of how a system works, such that you could simulate out over time what its behavior is. And we'll be seeing how the tools of system dynamics can be used to characterize a system, as well as to be able to analyze what's driving that behavior, sort of the impact that certain variables within the system, certain factors may be having on overall system behavior. The second type of simulation we'll be talking about is a simulation known as agent-based modeling. And in this type of simulation, we're characterizing, again, how this system works. We're positing sort of a theory that we operationally capture in a model about what's going on out there, what's influencing what and how much. But we're doing so at a finer grained level, at a level whereby we are capturing individual actors within the system. If we think about a population of people, those actors might be people, but they might also be other actors such as a city government, an organization like a company, the set of individuals associated with a school. And here we're simulating the behavior over time of this system in a way that captures the interaction of these actors and helps us understand how that interaction leads to certain patterns of behavior we see and how we might be able to influence that by intervening in certain places within the system. The distinction here from the system dynamics modeling we talked about earlier is we're actually distinguishing particular pieces of the system and talking about their interactions. The third sort of simulation that we'll be discussing is a type of simulation we'll be looking at very briefly within the course, and specifically in the later areas of the course. You'll see it highlighted about 3/4 of the way through the syllabus, through the outline and topics cover, which is a type of simulation called discrete event modeling. Discrete event modeling is, of the three, perhaps the most widely applied, but the most narrow in its focus. The goal with discrete event modeling is to characterize a set of processes that operate on fairly passive actors that come in. So maybe you're characterizing a set of processes that go on an assembly line of cars. And each car that goes through gets assembled piece by piece by piece. But the attention is really not so much on the car, but on the processes that build up that car. Another example would be, think about people coming in hospital. Those people are operated upon, they go to the triage area and wait for the triage nurse to assess their condition. She asks them some questions. They go back and wait more, sometimes for many hours. And then eventually they get brought in and they get looked at by a doctor or something like that. And all along here, there's a set of processes that are operating on them. The view here is that these actors are more passive. They don't interact with each other except through things like cues. The fact that they have to wait because there's others ahead of them. And those individual actors are proceeding through the system in a somewhat passive way through various flows of different processes. So we have processes which may be branched, and sometimes they go one direction, sometimes they go the other. This form of discrete event modeling is very, very common for simulating industrial processes and for simulating flow of individuals in healthcare facilities, for example. And we'll be taking a brief look at that. We will further be talking in the later section of the syllabus, later section of the topics, on a set of cross-methodology topics where we combine these different types of modeling together. In a single model, we may have multiple types of modeling going on. And so we might use, for example, a system dynamics model to characterize an individual's biological response to some external stimulus, and that individual is located in a network characteristic of agent-based models. So we're going to be looking at how we can combine together techniques. And then in the final section of this syllabus, we're going to be examining a set of processes that we undertake in modeling that are common to all of these different approaches. And those processes include things like sensitivity analysis, like calibration, whereby we estimate certain parameters of models, and certain types of analysis and reasoning about models, and some best practices for building models. So this course consists of coverage of 3 types of modeling. Most of the time is spent with agent-based modeling. There is a significant amount spent with system dynamics and just a little bit with the discrete event modeling. I'm having some trouble getting this thing up on the screen, and I'm just trying to figure out why here. So I apologize for crouching down here. But for some reason, it's not displaying as anticipated. So I may have to just post these slides and simply talk about them here. Okay, so let's talk about some aspects of how I'm anticipating running this class. This class is going to be an interesting hybrid this term between 2 types of approaches. On the one hand, we're going to have a lot of lectures which are delivered as such. So I'm going to be speaking from slides and going through a set of material, pausing to break it up into sections which can then be individually uploaded so that you can get finer-grained access to my material. So that's one set of approaches I'm going to be using during some of the sessions this term. For other sessions, there's going to be existing material that I'm going to point you to ahead of the class. Okay? So these are going to be material that's available through my lectures that are online on YouTube already. And for material, I have some videos already available which you could review. And for those cases, what I'm going to try to do, not every time, but for a lot of the times, is ask you to undertake some very simple exercises when you view it. And the idea here is to make use of what's called a flipped classroom. Is anyone engaged here on campus in a flipped classroom experience? Okay, I'm not familiar with that. So the idea is ahead of time you folks review the videos, okay? Videos like that you can view from any number of places. You don't need to come here to hear me deliver them. But when you come here, we're going to take advantage of our unique joint presence in this classroom or electronically together. How are we going to do that? What we're going to do is we're going to use that time to help students undertake exercises in class, which will advance your knowledge, and will allow you to ask questions about the applications of these materials or confusions about these materials from having tried to do these exercises at home. So the idea is to use the classroom for the unique advantages that it offers in the form of ability to ask questions, in the form of ability for me to look at what you're doing when you're doing an exercise and for me to give you pointers, and the ability to pursue your projects. So for those who are pursuing projects, we can use some of that class time to advance your projects, get you unstuck from certain things, help address questions, etc. So this class is going to have some sessions that are more traditional and lecture-based, starting with this one. It's going to also have some sections that are very fluid in the sense that I'm going to be walking around, seeing how people are doing, answering questions, and sometimes popping up to give a little bit of a lecture that will address student confusions. So those are the two forms of lectures. Now I'm anticipating roughly half-half, okay? So there'll be some that are very interactive and some that are more lecture-based. Okay, so that's just some aspect of the flipped classroom environment. This class is very diverse. The set of people in here in this classroom come from all different areas of campus. The students who are from an undergraduate background are predominantly coming from computer science and engineering. The students who are from a graduate background are predominantly coming from from areas outside of arts and science, although some are from this department as well. And as a result of this, there's going to be students with very different levels of exposure to certain types of material. I'm dealing with that in two ways. First thing is the undergraduates and graduates have different expectations. The second thing is for graduate students, I'm going to be having extra sessions, which will address some needs there. The third characteristic by which we're addressing this is we're going to try to make sure that the students, when they ask questions here in class, get answers tailored to their background. So sometimes I'm going to be answering questions for students that may be familiar to some of you, but unfamiliar to others. And that's going to be a reflection of the fact that there's diverse backgrounds. And sometimes I'm going to be saying something which is old hat for some, but very new to someone else. And I'd ask for your patience with that. Okay, so it's going to be a diverse class. There's going to be some stretching involved. Stretching in the form of pushing yourself methodologically on some types of material that may be unfamiliar to you. This would include some aspects of mathematics for both the undergraduates and the graduate students. It will also include some material on domain applications. So we're going to be talking quite a bit about health applications of models. How do we use these models to improve decision-making associated with the health area? Health is something, the health area and the healthcare system is something more familiar to some students and not to others, so we're gonna ask some students to stretch themselves in that regard. Okay, the most important resources that I'd like to refer you to are listed here. And the first of them is probably the most important other than the course site itself. And that's this link here, so Consensus ABM. I'll be posting this on the site for the course, the Moodle site. But the Consensus ABM site is going to provide you access to a broad set of videos that I'm going to be recurrently going to request that you watch. It will also provide a lot of extra reference material for stuff in this course. If you went to this site and reviewed material accessible on that site through that URL, you'd learn, you'd get a very strong glimpse of what's to come and an understanding of much of the material. There's lots of things there I'm not going to have time to cover, but they go into it in more detail on the site, etc. So this is my site with lots of videos there that you can find of relevance. And I'll be sending out mail suggesting you watch particulars of this video, but if you go there, you'll find alternative videos to the one that I'm sending out, videos that may go into more depth, etc. So that's one issue. Second issue is office hours. I'm going to be offering office hours directly after class. We're going to see if, because it gets late after class, we're going to see if we can have some additional time for office hours as well for this course. And finally, there's going to be some focused tutorials. For those not from computer science background, this is going to include some programming assistance and understanding. For those from computer science background, we may have additional tutorials on subjects that are unfamiliar to you. How many students in here are from engineering background? Okay. So you students are probably going to have the strongest methodological grasp of what's needed here, because there's certain things you will have seen before that computer science students wouldn't necessarily have seen on the math side. So there's certain aspects of applied math in the form of differential equations that we're going to be asking people to develop comfort in, and I'm going to be providing the support needed for that. But the engineering folks will have seen this enough times that it won't be anything too new there. Okay, so what's expected of you? Attendance and participation. This should be an interactive class even for the lectures. Viewing of online materials to supplement class lectures where required. Assignments for those students who elect that option. And for the students who elect the option of a project, that is as well. For those who elect a project, willingness to use computational tools, the simulations here, for areas that are of interest to the stakeholders. So that's going to involve some learning. Okay, so there's going to be a fair bit of stretching all along here. So in terms of the projects, I strongly encourage, per my comments earlier, multi-person projects. I'd like to encourage students to work in teams, and ideally interdisciplinary teams. Take advantage of the diversity of this class. Some people are going to be students in this class, but can also provide guidance as to a project. So there's a great opportunity here to do amazing things which no one person on a team could have done in isolation, where the whole is greater than the sum of the parts. And that, indeed, folks, is a theme of this course we'll come back to probably later in the session. In some sense, this class is about the science of the whole. Science of situations where the whole is greater than the sum of the parts. Situations where any one piece doesn't explain it, something to the sum of the pieces, it's interactions. And one of the best places you can see this is projects from this course. So we have recurrently had from 858 and from 394 projects which come out of this class that could not have been done otherwise. I mean, they're amazing things, publication worthy, etc. And if you want to make contributions that, say as an undergraduate, that could get to the point of publication, this course may be the best chance you have in an undergraduate education of doing that. So the project can be, for those who choose to undertake it or considering it, the project can be a modeling application. It can be a methodological study. You may compare, for example, two different frameworks for doing agent-based modeling and critique each of them. Or it may be building a model to study something. Perhaps, for example, building a model to help us understand how H1N1 spreads within Saskatoon. How the current outbreak of H1N1 in town is predominantly spread, and what we can do most effectively about it in terms of vaccination. So my job as instructor, for those who are considering projects or going to do them, is to facilitate that. And that takes a lot of my time and energy for this course. So if you're going to do a project, I'm there to back you up, but you should view it as a substantial commitment of time. One that takes you away from assignments, yes, and decreases your time there, but it's going to require at least that amount of time in delivering the project. You're not going to be saving a lot of time for yourself by not doing assignments. In fact, you'll probably have to do more work in terms of the project. Please get started early on this, and again, I'm going to be delivering to you probably by next lecture before the list of projects which I'd like to suggest, okay? And the projects, we're shooting for projects with stakeholders. In other words, with someone who cares about the outcome. It's not merely something of interest purely for the sake of this course, okay? So stakeholders interested in using this, taking it further, We've had corporate stakeholders, we've had stakeholders who are from zoos and are interested in understanding how to better manage disease in their zoo population. We have had people who are from policy background and want to understand how to lessen certain health burdens. So the project components involve creating a simulation, placing data into the model to customize it to a particular context where that's possible, running a baseline scenario that sort of describes the default situation, a reference point, and then some what-if scenarios to provide sort of alternative situations. If we did this, how would it be different? Simulation models provide some of their greatest power by allowing us to ask these counterfactuals. If things were different, how would what we see change? How would it change the dynamics of the system, behavior over time? That's what a lot of these simulations are used for, and they're used to inform decision making because we're asking what-if questions about different options, different choices we have. So a big goal for the project would be if we could run alternative scenarios that kind of said, if things were this way, how would things be different? So it should include some components that we should have some sensitivity analysis. In other words, with these simulations, sometimes, often, typically, we don't have perfect knowledge to allow us to describe the system. We're uncertain about certain things. We think this is how it works, but we're not certain. Or we know this is how it works, but we're not certain how much the certain factor is involved. And we can do sensitivity analyses, they're called, to sort of shed light on that. To shed light on, for example, does this uncertainty about this factor really matter in terms of the things we care about, in terms of our choices? There'll need to be a written report handed in a 30-minute presentation, ideally in class, although we may have to defer those to summarize the model, its construction, and findings. Okay? So again, best done with multiple people, but these are the sort of pieces that would be required for a project. Okay, we will further be pursuing modeling exercises here in class. And I'm going to be going around and help people where they get stuck. It's a great chance to kind of try out that knowledge that you gained via video before, that you've just heard in class, to try things out. Now, I need to know something. One of the reasons I'm mentioning this right now is I need to get a show of hands. How many people in here would like a computer delivered to this room for you to use for these exercises during this classroom? In other words, how many of you aren't going to bring your own but would like a computer brought for you? Anyone? Okay, so so if we had 4 or 5 computers brought, that would be great. We have computers installed here in the department with software. There's 2 software packages we're going to be using, AnyLogic and Vensim, and we have the portable lab that can be brought here. So we'll see if we can get these computers, laptops delivered here. If there's anyone who didn't raise their hand and would like to later request it, feel free to do so. One of the things I'm going to be doing after today's session is send mail to you for regarding the software that you can use, where you can download it. Okay. The software does run. One of the packages, AnyLogic, runs on Linux, Mac, and Windows. The other software package runs on Mac and Windows. So if there's anyone running Linux, you'll want to run one of those pieces of software in a virtual machine. Okay. So that would be something to think about. Again, we can get the laptop delivered for you. Okay, so office hours, as I said, Tuesday, Thursday after class, and it's in my office. But I'd like to encourage people to meet with me by appointment as well. And I'll try to announce another sort of regular time so that we could get to it. So I have some links here, but I'll post these to the website so that you could see them. I can't provide the AnyLogic download, so I used to put the URL for AnyLogic here, and but then there was was kind of cognitive dissonance. I wasn't thinking it through. I put the URL here, and then I uploaded these slides to the web. And so, so folks from the AnyLogic company saw my slides, and they said, "Hey, you're giving out, free downloads of our software." And I said, "Okay, yeah, I'll take it down." So I couldn't put it up on the web. I'll be sending a link, but it's actually a multi-stage process. So this is a bit of administrivia about the course, a bit of description of what you can expect from this first course, session. Are there any questions about that before I go on to more substantive material? Our first sort of discussion about what it is we're going to be looking at in this course and why we're looking at it. Any questions? Yes? We will be talking some. So turns out that some of the models that we'll be looking at directly, so the same model is used in health sciences that are used in non-health sciences is one area. But we'll also be talking about some specifically non-health related models as well. The ones that are dual are of particular interest because they're very general models. In other words, they can be used in area X, Y, Z, ABC. And they include models, for example, used in marketing, models used in penetration, in understanding, for example, company growth and the number of items sold by a firm. And so the exact same model structure goes by different names. In health area, it goes by the SIR model. In non-health area, it will go by different names. Fast diffusion model is one of the more common names. And we will be talking about those sort of models. We will also periodically discuss ways in which, a health perspective would have certain concerns, but if you were doing modeling in a different area, say associated with the corporate world or what have you, what the different needs would be. But I do want to emphasize one thing related to this. This course deals explicitly with building tools, simulation models, that help us understand phenomena in the world, right? We understand phenomena. Those phenomena could be of any different sorts. One use of these models is to simulate computer systems. In fact, they're very, very attractive for understanding the performance, for example, of larger scale farms of servers, or the performance of something like YouTube under, while millions of people are hitting it for different videos and so on. People use these sort of simulation models for that purpose, and that's an application whose domain of application is closer to computer science. These same models secure use in, same type of model will secure use in the health area, in environmental areas, in simulating people's movement through cities, in simulating the competition of companies, in simulating the movement of armies, all sorts of things. So we're talking here about a tool that's computational in nature, a tool that you build on computers, that's a computer program whose job it is to inform decision-making in other domains. The health one will enrich it because we'll be talking about some aspects in depth, but some of these other domains will come up periodically. But we are fundamentally talking about application of computer science principles. The underlying tool it comes out of computer science. It's just domain of application is different. Okay? So other questions? Okay. So I'm going to stop the recording for this, and we'll start up a discussion of some of the